Welcome back. So limits and continuity by example. I did a pretty lengthy video on limits and continuity as an introduction. And it did cover the exact topics that you see here on the screen. So when does a limit exist? And then when is a function continuous at x is equal to a? I went over that. So I'll put up a link up above there if you want to go over that entire introductory video. It is a lengthy one. In here, let's kind of get started and summarize. So on the left-hand side, you see the summary of the when a limit exists. And on the right-hand side, it has that introduction to, continuity. Okay, so first of all, a limit, okay, as x is approaching a, of f of x exists if three conditions hold. Now, these three conditions that we have, the first two conditions, again relate back to a limit, except you would have a limit approaching from the left-hand side, and then the second one is you would be having a limit approaching from the right-hand side. And again, so what will that mean? And hence, that's why I labeled this, by example. So I want to be able to go into this by example, okay, in terms of summarizing these. Now, once we find the limit from the left and then we find the limit from the right, okay, as they're approaching, and if they basically are equal to each other, so once we find these two, then we say that a limit exists at a, okay, so as x is approaching to a. So I have that as my third condition. So those are the three things. Okay, does the limit exist from the left? Does the limit exist from the right? If that is true, number three is, are they equal? And if they're equal, then we're done. Now, for the continuous case, so if we wanted to know if a function is continuous at x is equal to a, again, we need three conditions. And the three conditions are, we have to make sure that a is actually in the domain of f of x. So that means that f of x is defined at x is equal to a. Because if it's not, then there's nothing to talk about. So that's number one. Okay, so is f of x defined at a. Now, the other two conditions actually relate back to the left-hand side that you see there on the table is with regards to limits. So a limit has to exist as x is approaching a. And if it does, okay, so that would be our second condition. So we would need the left-hand side to hold entirely, okay, of this table. So you see there, those three conditions on the left. If they hold and your function is defined at a, so a is in the domain, then we have to check, is the limit itself, okay, not only does it have to exist, but is it equal to the function at a. So we would substitute the a into the function and we're going to check, are these two actually equivalent? And if they're equivalent, then we say that it is continuous at x is equal to a. So those are the two key things, limits and then continuity. Now, very often we run into the case where we say a function, so some function, is continuous. Okay, so we say that. Now, beforehand, when you were studying in grade 11 and then maybe in advanced functions, you had some sense of continuity, right? And discontinuity. And I can put up a link about the discontinuity up above there, okay, if you want to go back to that and then think about it visually. But in here, we can now really talk about what does it mean for a function to be continuous. What it means is that the three conditions that we outlined for continuity, okay, so these three conditions here on the right-hand side, those conditions only hold for one point, right, for x is equal to a. But if it is true that they hold for all of x, okay, on the real number line, so basically the entire domain has to be defined, and then there is a limit for any single x that you like. And not only that, okay, f at that point has to equal to the limit for all of x. Then we say that the function is continuous. And you're going to be running into this quite often. Now, for many cases, it's simple to understand. And I hope that as you're introducing yourself to calculus, you'll start off with very simple functions, and then you progressively are going to make them a little bit tougher. But there are some subtleties, okay, that we have to think about. Now, let's think about this, on the left-hand side and then the right-hand side. Okay, again, let's go back because I labeled this limits and continuity by example. So let's take a look at this through some examples. And I'm going to go back in here just so that it refreshes our mind so that we know what to do. Now, this function is a piecewise function. So it is made up of two pieces, okay? So basically, as you can see here, okay, so it's made up of one piece. This is really just a line, which is defined for x is less or equal to 1. And then it is defined of a second piece right here, okay? And this function looks like it's a quadratic, okay? So it just looks like it's just been shifted, okay, to the right, okay, by 1. And it's defined on x is greater than 1. Now, let's take a look and think about and talk about these limits and then the continuity. And I want to be able to define certain things. So first of all, okay, we're going to want to be able to talk about this. So let's say x, and I'm going to be purposely, taking x and let's say, does the limit as x is approaching to 1 of this function, so f1, okay, does this exist? And if it exists, what does this actually equal? So let's take a look at this. Now, I can pop up decimals and make it visual, but I can also draw this. This isn't actually very difficult to draw. Okay, so this particular function. So here, if I have my x and my y-axis, actually this one I can bring down because of the fact, okay, that I can see that it's defined up on these. So, let's make this, for instance, 1, this would be 2, this would be 3, this would be 4, and so on. And this is 1, and this is 2, and this is 3. So 1, 2, and 3 going up. Now, for this function, so because it's just a line, so notice it goes through 1. Maybe I'll take a different color here. And it will be going, okay, so it goes through right here. The other point, so it has a slope of -1. So I can put another point here, and it is defined right here. So I know that this line basically, okay, is going in this direction, and it's going off into there. Now, the second line that I have, so this one right here, so this is just a quadratic, okay, so that's a parabola opening upwards, but it is being shifted. So notice this, it has a translation there, okay, so it's been shifted. So this kind of looks like this. It's going to, start from over here. However, it's not defined right here. So we put an empty there, and then it just keeps blowing up on us right here. Okay, so this is going to blow up. Whoops, it's going to blow up in this direction. So it's kind of going to look like that. And now, if we want to talk about the limit, so we need the three conditions. So the three conditions, well, the limit from the left-hand side, the limit from the right-hand side, do they exist? And then my third condition is, if they do exist, are they equal to each other? So let's make this visual this time around. So from the left-hand side, I can see that I'm going to be approaching, okay? So I'm going to be going in this direction, okay? And I am approaching here, as I make it closer and closer, it looks like the limit as x is approaching 1 from the left-hand side of f1 at x, this looks like it's going to be equal to 0. All right? So that's what we would have. Now, from the right-hand side, what we would have is, so if we're going and we're approaching 1 from the right-hand side, notice it's not actually defined, right? It's not defined there. But we can approach it and get closer and closer and closer together. And we can see here that also the limit as x is approaching 1 from the right-hand side of this, okay, function is also exists, and it is 0. Now, because these two are equivalent, we would say that the overall limit does exist and it is equal to 0. That's what we would have. So those would have been the three conditions. Now, in the introductory video, when I was talking about this, you can also do it algebraically, okay, and I showed you there how. Here I wanted to also do it, make you and see the actual graph and see it visually how it happens. So that's what you would have there. Now, if we wanted to know continuity, so what we would have to have is, okay, so if I go back in here, so I need these three conditions. I need the function to be defined at my a, in this case that would be 1, and it is defined, all right? So if I would take this f at 1, okay, so like so, well, if I go in here, I look that is just equal to, so we would substitute 1 for x, and this would have been plus 1, so this indeed just equals to 0. I just found out, so that was my condition 1, so this is satisfied. My condition 2, I needed to know if the limit as x is approaching 1 of the function exists, and indeed it does exist, and we have shown just above there that it equals to 0. And then my third condition that I need is I need 1 and 2, so I need these to be equivalent, and they are. Okay, so that means 0 is equal to 0. So the limit as x approaches to 1 of that function is equal to the function at that point. And that would have been my third condition. And now we would say that the function is continuous at x is equal to 1. That would have been true for this. Now, if you wanted to ask the question and say, is this function continuous? Okay, period, so meaning is f1 at x continuous? That means that this would have to hold for all the points. Now, as we can see, that this function, okay, because there's no official, restriction, so from negative infinity to positive infinity, it is defined for all x, so that is true. And really the only problem does happen, okay, at this point where we have one piece of the function interacting with the other piece. And we have just shown that it is continuous at that point. At every other point, it's going to be, so on the to the left of 1, okay, it's basically just this. And that is just a simple line, so it is continuous on every point there. And on the right-hand side, it is equal to this, which is a quadratic. And a quadratic is also continuous at every single point. There is nothing wrong that is happening. It's defined, right? The limits would exist, okay? So we wouldn't have anything to worry about. So this function, although it's piecewise, it is actually fully continuous from the viewpoint of the conditions that we have. Now, sometimes your teachers may want to know a full-out explanation of this, and you would actually have to write it out and then present it, okay? And what I recommend is, you would present it from the viewpoint of these 3 points. And then you would argue with regards to these points if the function is continuous or not. So that's one example that we would have. Now, here is a very similar, so it's basically the same thing. And what I have done is I have just, taken my quadratic. And again, I have just translated it. I just moved it up. Right? So just moved it up by 1. So let me just draw it quickly. Here it is. All right, so here are my 2 pieces. This is my piece 1, so that's the one to the left. So that's this one right here. That's what you would see there. And then this one is to the right. So here's my piece, okay? So it's a quadratic. That's what we would have there. And with this particular function, so we can visualize and see what is happening here. Now, again, let's go back and talk about the limits and then continuity with regards to this. So in here, what we would have is, if we were chasing this down, so it will not change, right, our limit as we approach from the left-hand side. So our limit from the left-hand side, as we just have done it, it still is equal to 0. Now, here, at the limit from the right-hand side, as we're approaching in this direction, Well, we can see that basically that limit is going to be approaching 1. And now, you can make it very formal, right? So you can say limit as x is approaching, okay, this would be 1 from the positive side, and here is my function, so x minus 1 squared plus 1. You can make it from the right-hand side, so if you recall, you can say, this would have been, you can substitute, okay, for x, you can say 1, because we're approaching 1, and it is plus some h, and then h is tending towards 0. So in that case, if we would substitute this back in there, okay, and then we would do the arithmetic, well, in this case, you would see, and I encourage you to substitute this in, make h go to 0, you would see that that substitution is going to yield for us 1. That's what would happen. Because of the fact that this actually would disappear, so this is going to tend towards 0, okay, if you substitute this and let h equal to 0, so all you would have left is just that. So from this, even just visually, you can see, well, the left-hand limit does not equal to the right-hand limit. So right away, we know that the limit itself does not exist. So the limit as x is tending towards 1, okay, of, well, in this case, this would be f2, okay, does not exist, okay? So that is how you can show it. And if the limit does not exist, then clearly the function will not be continuous, because that's one of the actual criteria that we need for continuity, right? It is actually defined at x is equal to 1. It's still equal to 0. But that second criteria that we have for continuity is that we need the limit to exist, but the limit does not exist. So we don't even have to go to the third criteria, are they equivalent? Meaning the function at 1, okay, does it equal to the limit as x is approaching to 1? No, because there is no limit, okay? It doesn't actually exist. The left-hand side limit exists, the right-hand side limit exists, but they're not equivalent. So therefore the limit does not exist. So that would tell us that the function at 1 is discontinuous, right? It's discontinuous. So there's a discontinuity. And if you remember from the functions course, that should not surprise you, because indeed it is very clear that this function is actually broken here, right? So it is clearly broken right here. So if we, take a small little circle, we zoom in here, right? We have a discontinuity. So this function, we can draw a line in between, and it will just separate the two pieces completely apart. Okay, so that is discontinuous at that particular point. Now, here's another example of basically the same thing. So it's the same function, except now I've included 3 pieces, but one of the pieces really is just a point. So we would have exactly the same thing as we have above here, but we would have a point. So let me just clean this up. All right, so now it's all clean. So this is exactly how it would look like. And again, it should not shock you. It's now very visual, so you can see that in this case, this function is discontinuous, right, at 1. So at x is equal to 1, okay, it's completely discontinuous. Now, again, we can find the limits. The limit also does not exist, because if we're going in this direction, okay, the left-hand limit would be 0. If we're going in this direction, okay, the limit would be 1. So those are not equal. So first of all, the limit does not exist. And also, okay, notice that we do have, okay, our function being defined at f. Okay, this would be 3. Sorry, not at 0, but at 1. Okay, but it is equal to 2. So it doesn't even equal any of the left-hand or the right-hand limits at all. So clearly this would have been discontinuous. So that's another example. These are all different examples, and I like the piecewise functions to illustrate this because it's very, nice to be able to see the different varieties. Okay, so this is just a summary, again, and with 3 examples. And I hope that by seeing a couple, of videos, the original video on the introduction to this topic, where I did a lot of examples, made it algebraic, now I made it visual and then summarized the limits and continuity for you. You kind of get some intuition behind what happens with these functions. All right, thanks for watching. We'll see you in a future video. Okay, happy studying for calculus. Cheers.